You know, people ask me all the time if they say, Feynman, is the electron in my hand the same electron as the one in the star a billion light years away? And I say, well, that's a damn good question. Because when you really sit down and think about it, and I mean really think about it, not just nod your head and move on, the answer leads you somewhere so strange, so utterly breathtaking, that most people, when they first hear it, don't believe me. So let's talk about it. I want you to imagine you're looking at two electrons, two tiny, tiny particles of matter, each carrying the same charge, each with the same mass, each spinning in the same way. You cannot tell them apart. And I don't mean you can't tell them apart the way you can't tell apart two marbles that look similar. I mean something far more profound. I mean that there is no experiment, no measurement, no trick in all of physics that can tell you which electron is which. They are not just similar, they are identical. And that word, identical, has a meaning in quantum mechanics that it simply does not have anywhere else in ordinary life. Now, in classical physics, the old physics before we knew better, if you had two billiard balls, even if they looked the same, you could always in principle paint one red and one blue and follow them around. You could say, this one started here and that one started there. There was always a way to keep track. Identity was something you could hold on to, but electrons, you cannot paint them. You cannot tag them, you cannot put a little label on one and say, this is electron number 1, because the moment you try to do that, the moment you set up any experiment to distinguish them, nature itself refuses to cooperate. The laws of quantum mechanics are written in such a way that the two electrons are fundamentally, irreducibly, cosmically interchangeable. And this isn't just a limitation of our instruments. It's not that we don't have good enough microscopes yet. It is a deep feature of reality. The universe, at its most basic level, does not assign serial numbers to its particles. Now here's where it gets interesting, and I mean really interesting. There was a time when I was working on quantum electrodynamics, and my old teacher, John Wheeler, called me up. Now Wheeler had this way of calling you with an idea that sounded completely insane, and then turning out to be half right, which in physics is actually pretty good. He called me and he said, Feynman, I know why all electrons have the same charge and the same mass. And I said, why? And he said, because they're all the same electron. Now I laughed. But then I stopped laughing, because the idea, when you unpack it, is one of the most extraordinary things I have ever heard. And I want to explain it to you. Here's the picture. In quantum mechanics and in the theory of relativity that we weave together with it, a particle moving forward in time and an antiparticle moving backward in time are mathematically the same thing. I know that sounds like I'm playing games with words. I am not. This is real mathematics, real physics. An electron going forward in time looks exactly in the equations like a positron, the antiparticle of the electron, going backward in time. So Wheeler's idea was this: what if there is only one electron in the entire universe, just one, and it travels forward in time, zigs and zags, goes backward in time as a positron, forward again as an electron, backward again, weaving through all of space-time like a single cosmic thread. And at any given moment, the moment we call now, that thread crosses the present moment billions and billions of times. Each crossing point is what we call an electron. The places where it goes backward in time we call positrons, one thread. Infinite crossings, that's the whole universe of charged particles. Now, I told Wheeler there was a problem with this. If there's one electron zigzagging through time, then every time it goes backward, it appears as a positron. So there should be exactly as many positrons in the universe as there are electrons. And as far as we can tell, there aren't. There's a profound asymmetry. The universe is made mostly of matter, not antimatter. And we don't fully understand why, by the way. That's still one of the great open questions in physics. So Wheeler's one-electron universe probably isn't literally correct. But, and this is what I want you to hold on to, it doesn't have to be literally correct to be deeply illuminating. The idea points at something real. It points at the fact that in quantum field theory, the modern framework that replaced the old picture of particles as little hard balls, electrons are not objects. They are excitations of a field. Let me explain what I mean by that. Think of a field as something that fills all of space. Every point in space has a value, like temperature. You can talk about the temperature here, the temperature over there, the temperature everywhere. Now imagine something like that, but for electrons. There is an electron field that fills the entire universe. It's everywhere, always. And what we call an electron is a little ripple, a little disturbance in that field, like a wave on water. The water is the field. The wave is the particle. Now here is the key point. When you have two ripples on the same water, they are ripples of the same water. They don't have individual identities that come from somewhere else. They are modes, they are patterns of one single underlying thing. And that's why all electrons are identical. They are all ripples in one electron field. They all look the same because they come from the same source. The field has a particular character and a particular set of properties, and every excitation of that field inherits those properties exactly. This is why the electron in your hand and the electron in a distant galaxy have exactly the same mass, exactly the same charge, exactly the same spin. Not because the universe is being very careful to manufacture them to spec, but because they are not different things. They are different expressions of one thing. And this changes how you think about particles completely. You stop asking, where did this particular electron come from? And you start asking, what is the state of the electron field in this region of space? That's the right question. The particle isn't a thing that travels from place to place and has an identity as it goes. The particle is what the field is doing right now, right here. Now I want to talk about something that follows from this, something called the Pauli exclusion principle, because it is one of the most important and most misunderstood consequences of particle identity. Wolfgang Pauli, a brilliant and, I have to say, somewhat frightening man, figured out in 1925 that no two electrons can occupy the same quantum state at the same time. Same position, same momentum, same spin, impossible. The universe forbids it, and for a long time, people learned this as a rule. You memorize it, you use it to explain the periodic table, you move on. But the deeper question is, why? Why does the universe have this rule? And the answer is hidden in the indistinguishability of particles. In quantum mechanics, when you have two identical particles, the wave function, which is the mathematical object that describes the quantum state of the system, has to behave in a specific way when you swap the two particles. You have two choices. When you exchange the particles, the wave function can either stay the same or it can flip its sign, multiply by -1. These two options correspond to two fundamentally different types of particles in nature. Particles whose wave function stays the same under exchange are called bosons. Photons are bosons. The Higgs particle is a boson. These particles love to be in the same state. In fact, the more of them you put in a state, the more likely additional ones are to join. This is why lasers work. A laser is essentially a situation where you've convinced an enormous number of photons to all be in exactly the same quantum state, because bosons have this gregarious collective tendency. Particles whose wave function flips sign under exchange are called fermions. Electrons are fermions, protons are fermions, neutrons are fermions. And here's the thing. If two fermions were in exactly the same quantum state and you exchanged them, the wave function would have to simultaneously equal itself and the negative of itself. The only number that equals its own negative is 0. So the probability of finding two fermions in the same state is 0, exactly 0, absolutely forbidden. That is the Pauli exclusion principle. It's not an extra rule that was added on top of quantum mechanics. It falls out of the mathematics the moment you take seriously the fact that electrons are identical particles. And the consequences are staggering. The reason atoms have structure, the reason electrons occupy shells, the reason chemistry exists, the reason the periodic table has the shape it has, the reason molecules form, the reason you are not a formless blob of matter. All of this traces back to the fact that electrons are identical fermions. Because if electrons could all pile into the lowest energy state, they would. And matter as we know it would collapse. But they can't. So they stack up, each in its own state, like books on a shelf, and the architecture of matter emerges from their stubbornness. The solid ground beneath your feet is solid in large part because electrons refuse to be in the same state. There's a name for this. Electron degeneracy pressure. And it's not just poetic, it's what holds white dwarf stars up against gravitational collapse. Dead stars, dense beyond imagination, are held together by this one quantum mechanical fact about identity. Now I want to come back to the question we started with, but approach it from a different angle, because there's something philosophically remarkable here that I think deserves a moment's attention. We are used to thinking that the reason all electrons are the same is that they were all made by the same process, stamped out by the same machine, so to speak, like coins from a mint. And while that's not a completely wrong intuition, it misses the deeper point. The deeper point is that identity in quantum mechanics is not just a matter of having the same properties. It's a matter of being literally interchangeable in the wave function without the wave function knowing the difference. Here's an analogy. Suppose you have two music notes, two perfect A440 tones playing simultaneously. Can you say which one is note 1 and which is note 2? There's no sense in which that question has an answer. They are not two separate things that happen to sound the same. The sound field is vibrating at 440 hertz, and we're asking for two of them, but those two aren't individuated. The notes don't have identities. The field just has an amplitude. Particles are like that. They don't have hidden name tags. They don't have serial numbers that are inaccessible to us, but exist in principle. The identity is absent in a fundamental way. Not hidden, not encrypted, but genuinely not there. This is one of those places where quantum mechanics forces us to revise something we thought was obvious. We thought that objects have identities. We thought that if you have two of something, there is a this one and a that one. And in everyday life, this is so reliable a feature of experience that we never question it. But everyday life is built out of enormously many particles, and the quantum strangeness averages out. When you get down to the level of a single electron, the ordinary intuitions fail. Not just fail to apply well, they fail completely. There is no this one. There is no that one. There is just the field in a state that involves two excitations, and the excitations are not further individuated beyond that. Now let me talk about something even stranger, because I can't resist. There's a phenomenon called quantum entanglement, and it is intimately related to everything I've been saying. When two identical particles interact, when two electrons, say, scatter off each other, something happens to their quantum states that has no classical analog. The two particles become entangled. Their quantum states become correlated in such a way that you can no longer describe particle 1 independently of particle 2. They form a single quantum system, and because the particles are indistinguishable, you can't even say which particle went which way after the scattering. When you detect an electron going in one direction, you cannot say whether it was the original electron 1 or the original electron 2. The question has no answer. You've detected an electron. That's all you can say. This indistinguishability makes the calculation of what happens when identical particles scatter completely different from what it would be if they were distinguishable. You have to add up contributions from multiple paths. The path where particle 1 goes left and particle 2 goes right, and the path where they exchange. And because of the sign flip for fermions, these contributions can interfere with each other. This is called exchange interference, and it's a purely quantum effect with no classical analog at all. This is why the physics of a gas of electrons, what we call an electron gas, which is relevant to how metals conduct electricity, is completely different from the physics of a classical gas of distinguishable particles. The electron's indistinguishability changes the statistics. The statistics governs the distribution of energies. The distribution of energies determines how the metal conducts heat and electricity. The quantum identity of the electron, filtered through layer after layer of complexity, determines whether your phone battery charges or not. That's remarkable. That the abstract mathematical fact that exchanging two electrons flips the wave function, a fact about symmetry, a fact about identity, has consequences you can measure with a voltmeter. Let me tell you something about the way physics works, because this is a good illustration of it. In physics, we are always looking for the deep principle, the thing that explains the most with the least. And symmetry is one of our most powerful tools. When you say that the laws of physics look the same, if you rotate your laboratory, you get conservation of angular momentum. When you say the laws look the same at any point in time, you get conservation of energy. These connections between symmetries and conservation laws are deep and beautiful, and they were worked out systematically by Emmy Noether in 1915. And every physicist who knows the history knows that this is one of the greatest intellectual achievements in the history of science. The indistinguishability of particles is a symmetry too. It's the symmetry that says the laws of physics don't change if you swap two identical particles. And this symmetry has consequences. It gives you the distinction between bosons and fermions, which gives you the Pauli exclusion principle, which gives you the structure of matter. So the question, are we seeing the same particle everywhere, is really a question about the nature of symmetry in the laws of physics. And the answer is something like, we are seeing the same field everywhere expressing itself as particles. The particles don't have identities beyond what the field gives them.